Hello, friends. I know many of you will just skip those long programming time lapses to hear me talk, so let's do a review. As expected, the attempt was a failure. FPGAs aren't something you'd use to implement a game on directly. We implemented the heads-up no-limit poker game with the random player directly on the FPGA, and we even got the full throughput of the device by keeping the iteration interval at 1. But the consequence of that is that it ended up taking roughly half the capacity of the FPGA, which would have left very little room for something like a neural net. Even worse, in order to keep the pipelining optimizations running, the neural net would need to be duplicated dozens of different times in every place the action selection is being done. The reason for that is due to the fact that loop unrolling needed to keep the iteration interval at 1 ends up duplicating every iteration of the loop. For pipelining to work, it needs to allocate the hardware for each step, otherwise it cannot be done. Theoretically, we could try making an NN to replace the random player anyway, but it would need to be really tiny, so it would not be worth our time. Our approach is fundamentally flawed, but to begin with, this whole series was based on the desperation that we feel for better hardware, rather than cool-headed planning and reasoning. But the attempt wasn't all bad. Let us talk about some of the wins. First, during our work on the no-limit hold'em game after dealing with the merge sort, we had to work on random number generation in order to be able to sample cards from a deck, as well as sample random actions from a discrete distribution. What we found out when we tried synthesizing the RNG is that it is unbelievably fast. For example, generating random uniform floats takes only 3 clock cycles, and 2 of those cycles are subtracting a floating point 1 from the generated number to bring it into the 0 to 1 range. This implies that the RNG itself takes only a single cycle, which is amazingly good performance. The RNG isn't that straightforward. It does a lot of looping, exclusive ORing, and writing into an array. On a CPU, it would take at least dozens and more likely hundreds of cycles. Furthermore, sampling gaussians on an FPGA takes only 9 cycles. It seems it needs to allocate tables in block RAM for the cosine and sine functions, but 9 cycles is basically nothing. This experience made us realize that, if possible, we'd like to offload random number generation to the programmable logic fabric in the future, and it should be possible on the Versal chips. One final win that we have is the hand ranker function. Even though it has an elegant implementation in Spiral, the hand ranker for the poker game is a complex piece of code. It is more complicated than the game itself. At the start of the function, we have to do a merge sort for the entire hand, and afterwards we have to go through all 9 of the potential hand ranks in order to detect them. All of this requires a lot of looping, comparing, reading to and from the arrays. What do you think? How many clock cycles it would take? Our conservative guess would have been hundreds and probably thousands of cycles, given the sheer number of loops and the operations being done in them. How many did we get? We kid you not. We got 6. Hand ranking and comparing the poker hands should be done on an FPGA period. In the past, we saw some very complicated CPU-based hand rankers, which used hashing and had to pre-calculate large megabyte-long tables in order to break the million hands per second mark. But on an FPGA with very straightforward code, we could easily get hundreds of millions and billions of hands per second should we want to. It is crazy. We heard that the latency of going to and from the different components on a Versal chip over the interconnect is on the order of 30 cycles, so doing the hand ranking on the programmable logic part of the chip rather than the CPU would be a good use of it. We aren't really sure whether that is true or what the latency would be in practice. We just heard this figure being thrown about in a web presentation. We'll be verifying it in future videos. That covers all the wins. We went too far in trying to implement everything, including the game itself, in just programmable logic. We were angling to make the whole thing work on the older F1 FPGAs, but they won't be enough for what we want to do. The saying goes, only a bad artist blames his tools. People tend to think this means that the tools shouldn't matter and that a good artist should be able to make do with a bucket and a mop. But that is not true. What it really means is that a good artist should very well make sure that he has good tools. Right now, we are helpless. We might have some skill at programming. If we were arrogant, we could say we are the best. After all, not many people in the world could use functional programming to program GPUs and FPGAs. All of our past accomplishments, and all that pride and humility, those are just sentiments in the end. If we want to be the best, it should actually mean something. Being the best should mean having an advantage other people do not have, and we don't have it yet. So what we are going to do next in this series is take a break from programming the programmable logic. And we will focus on programming the CPU cores on a Versal chip, as well as the AI engines. Right now, we don't have access to those cards, but we have the VD's IDE, and it will allow us to emulate the needed functionality. If we implement the game on the CPU, the neural nets on the AI engines, while offloading the random number generation and the hand ranking to the adaptive engines, we should be able to gain something tangible, something we couldn't get by implementing such a project on a regular CPU and GPU-based system. We want to give programming heterogeneous systems a try. Spiral was originally created with such systems in mind. The fact that we got glued to high-level synthesis recently is only an accident. Where Spiral really shines is bringing heterogeneous together under one roof, and that will be the focus of our upcoming videos. Programmable logic will have to be a special case, but for devices like the AI engines, we should be able to make them dance with the integrated CPUs. Right now, we are mired in desperation and longing. We are longing for that special AI hardware to come out that would let us do AI in the way we want to. We keep yearning and waiting for it, living aimlessly, wondering whether at this rate the singularity will even happen. But maybe the hardware that we wanted already came out, and we just missed it. We have to make sure whether the FPGAs were the AI chips that we wanted all along. If we don't do this, then we cannot call ourselves living beings. If we miss the actual AI chips, what was the point of all our dreams and all our desires? Programming FPGAs over the past month definitely expanded our horizons and made us see programming in a way that goes beyond the confines of what we were used to. If we could make one more step, maybe we could become something. We should take courage and not give up here. The series will continue.